好，同学们，我们要开始上课喽。那么，如果大家有听不到声音，或者是有别的那个直播上面的状况，请大家留言。然后我在上课中，因为我是用全萤幕模式，我有的时候可能会看不到那个留言，但是我会检查一下。那么就请大家有事的话就留言。然后呢，okay. And today I am starting the lectures, and if there is some problem with the sound, or if there is some problem with the internet transmission, and you can just leave your message on the, I think it's on the right panel of the live stream screens. You can just leave it there, and when I see it, then I will try to do something with it. And then, before we really go into our lectures about physics, I would like to do a little reminder about the final exam. So here, this is our syllabus on the screen. And you can see that today we are here. Today it's the 4th of June. And the deadline of our final exam is on the 8th of June. So next Tuesday, 5:30 in the afternoon. So in this document, and I just gave you 3 choices, and you can pick your favorite one, and then please answer the questions in the instructions. And when you finish your report, and please just upload it on our New E3 website, and you can just read it through by yourself. And here are the formats, and please just keep your contents in the right format. And here are some rules. There are some certain cases that we'll just return your report, and we are not going to correct it. Here are a lot of students, and we have a very short time to finish the calculation of your final grade. So therefore, I'm afraid that we don't have the time to do the makeup session for you. So please just keep your report in the right format, and please follow the rules. And then I'm sure you're going to have a good ending for our course. And then I'm going to show you where to upload your report. So this is our new E3 webpage. We have a section here. This is the final exam. So if you click on it, then you're going to have a page for you to add your submission. So you just submit your report here and before the deadline, and here is the final countdown, so you can keep yourself in the schedule. Right, this is for the final exam. 好，那就是一个小小的提醒，我们的期末报告截止的日期是6月8号，时间是下午5点半，然后请大家把写好的报告，然后把它上传到我们 New E3 website， 它会有一个这边它会有一个栏位给你交报告，请你点进来，然后在这里交你的报告。那么我们也是在 New E3 我有上传一份文件嘛，然后跟大家说你可以选择报告的题目3选1，然后请你回答 instruction 里面问你的问题。然后我鼓励大家多多发挥自己的个人特色跟你自己的想法，对你这样做的话其实是比较符合我们的期望。那么最后还有一个小提醒，就是呢，因为我们通常在下学期的时候，我们考完期末考到我要把成绩上传到教务处的系统里面，那个时间很短，我们要赶那个大学4年级的同学要毕业的时程，尤其是我们现在交大跟阳明因为并校嘛，所以有很多医学、医事技术相关科系的同学，他们非常的赶，他们一定要在几乎6月中成绩就要结算完毕，他们才可以去考那个医事国考。 所以就搞得叫大家配合他们，所以我们也很急。那现在有一个状况就是呢，假设说你的报告里面出现一些令人无法理解的行为，我们可能就会直接把你的报告退回去，就不会再做批改。那我们时间紧迫，就没有办法再去跑一个问你为什么事情会变成这样啊，然后讨论有没有补偿的措施啊等等。下学期我们可能没有办法做这件事情，对，所以就是请大家在写报告的时候呢，要就是你的格式尽量遵守规范，然后呢，令人无法理解的事情，请你不要做。那基本上你到最后就是会顺顺利利的。好，那就是给大家一个小小的提醒。OK， 好，今天先这样。关于通知的部分，今天先这样。好，来，然后呢，我们要讲到物理学最有趣的部分了。So now we are at the gate to the most interesting topic in physics. It takes so much effort and so much knowledge for us to understand what's going on with quantum mechanics. So I've been teaching physics, general physics, for 3 years. Today it's the 3rd year. And every year I tried to push myself to teach faster and to keep more time for quantum mechanics, but I never really made it. And this year I'm in the same situation. When I just went through all the necessary knowledges before you can really get into the field of quantum mechanics, when I make sure that we are well prepared, then we are on the last day of the lecture. We don't have time, and we just have 2 hours to go through the math and go to the philosophy of quantum mechanics. I tried my best, and therefore I think today in the lecture I'm just going to do the introduction. Here are, of course, there are some calculations or derivations inside, but I am just doing it in a way like I try to point the key points out for you, and I'm just trying to tell you what the derivation is going on, and the details of the derivations, the algebras and the arrangement of the symbols and terms, and I think you can go through it if you need it later, or if you are learning solid-state physics. Yeah, I think for students in EE, at some time you have to learn quantum mechanics, because you have to learn quantum mechanics to operate the scales in solid-state physics, so that could be necessary. But when you really need the derivations and when you really need the scales, and you're welcome to come back to the slides and follow the derivations. Okay, so you can just download the slides and keep it with you, and you can keep it when you need it, and then you can see it. Good. So quantum mechanics. Here is a summary, or I would like to call it a roadmap of modern physics. So in the field of modern physics, and we've been struggling with a lot of difficult topics, and I just tried to do a little summary for those difficult topics, and finally we are coming to the math of quantum mechanics. And I'm going to show you some typical cases in quantum mechanics, and I think here are 4 basic models. We just try to simplify everything about quantum mechanics into these 4 typical models. So I'm going to introduce it, and here are the properties that we've been working on about the quantized energy for photons, for electrons, those charge carriers, and we've been working on it because we were struggling with black body radiation and photo effect. So this is also a topic about the quantized energy. And I didn't do the hydrogen atom here in this lecture, but I'm quite sure in the senior high school and you know something about hydrogen atom, and I think in the courses of chemistry, general chemistry, and there is a full introduction about the model of hydrogen atom. So if you need it, then you can try to remind yourself about it. And for the hydrogen atom, the topic about physics is about the quantized angular momentum of our electrons. So here is another parameter which is quantized. And then Compton scattering, we are talking about photons with the behavior of a particle, or they just transmit the energy, but you can treat the photons as a particle with a certain amount of energy and momentum. So this is Compton's achievement. Then here is someone doing the integration of everything. He tried to merge everything together, tried to create a general mathematical framework to describe light and particle. So this is De Broglie, and he just developed the concept of matter wave, and then he just tried to assign wavelengths to particles, and he just tried to explain what it is. And there are some other people like Bohr or like Schrödinger. They just said that maybe the wavelength of the matter is linked to the probability for existence. So that is another important topic. Then now we need a framework. We need a toolbox to do solid, to do accurate calculations, and we have toolbox. So we have a toolbox which is called wave function, quantum mechanics, developed by Schrödinger, and we have another toolbox which is based on matrix, and that is developed by Heisenberg. And Schrödinger and Heisenberg, they work separately. So they just developed everything by themselves based on different experimental results. And for example, I remember Schrödinger just derived the wave function based on the double slit diffraction experiment. Yeah, he just derived it based on it. And Heisenberg developed the matrix based on the optical spectrum of atoms. So he just developed everything based on the data from the experiment of an excited atom, and when the atom is relaxed, the electrons are coming back to the ground states, and it's emitting some lights, and then we just measure the frequency of all of these lights, and then we just draw a spectrum to describe them. And Heisenberg was deriving a mathematical tool for it. He is deriving the database of big data for the spectrum, and he is trying to look for the principles behind them. And in this table, you can see that there are particle-like properties and there are wave-like properties in different kind of interpretations, matches to either what particle-like properties or wave-like properties. Okay, so we are here, and we are going to introduce the wave function and the matrix. 大家等我一下，我喝一下水。我不知道为什么我的喉咙一直发出奇怪的声音，等我一下啊。好，应该可以。你等我一下，我去拿一下喉糖。 we start everything from Schrödinger's wave function because it's easier. The math developed by Schrödinger, it's easier for us to understand and easier for us to operate. And Heisenberg's matrix mechanics is a little bit complicated because it's handling a lot of parameters at the same time in the same matrix, and it takes a lot of time to understand how these parameters are related in a lot of matrices. So I decided to start from Schrödinger's wave function. And this is how the wave function is defined. So here, this is P. P is the probability. And we are in a three-dimensional space. And this is a little piece of volume. So this is the probability for a matter particle to exist. And the probability is just the square of the absolute value of a wave function. And this is just exactly the same. This is the little piece of volume. And the wave function here, you can always write it down in a form like a wave. So this is the complex form of a cosine or sine wave, and here this is related to the wave number, which is again related to the wavelength of your wave. And you can superimpose a lot of waves. So the form would be like you have the amplitude of a index I, maybe, and then this is the cosine and sine functions for the wave, and you have various wave numbers, k1, k2, k3, kn, and you just directly add all of these wave functions up. So you can just operate it like light waves, but the wave is not related to the fluctuation now. The wave is related to the probability for something to exist. So this is Schrödinger's idea. And how to really calculate it, how to derive those probabilities into something that you can measure. So this is what we do. We have the probability distribution, which is related to the wave function this way. And we would like to know that if I have a range of my variable x, the range is from A to B, and what is the probability for my particle to show them up in the range between A and B? And the probability is calculated this way. So this is a total probability. So if I don't care about the range A and B, I just care that from 0 to infinity or to a minus infinity to plus infinity, so which means the space is everywhere, the universe. And I just tried to calculate the probability for my particle to exist in the universe everywhere. So this is 1 by definition. So this is defined. You have to construct your wave function in a way like when I do the integration for probability in everywhere in the universe, and the probability should be 1, should be 100%. It should exist anyway. And then, now the thing is, I would like to know the position of my particle. I would like to know the momentum of my particle. I would like to know the energy of my particles. Then how do I calculate it from the probability? So we just use a concept in statistics. So in statistics, when we are handling the collective behavior of a lot of things and we are calculating the average value of them, we calculate the expectation value of them, and we calculate the variation of them. And now we are using exactly the same concept to calculate the measured value, measured quantity of our wave function, of our matter wave. Then this is how we do it. We do, for example, now we expect to see the position of my particle. So this is the expectation value. And I have a equation in mathematics, we call it operator. So we have we have an equation for the position. Then this is the wave function, this is the wave function. The star here means that we are taking the complex conjugate. Then complex conjugate is here. This one, this is cosine kx plus I sine x, and that plus sign should turn into a minus sign. That is complex conjugate. And then we just do the conjugate like this in a vector analysis, phi star something phi, which means that we are taking the magnitude of a vector. So it's equal to taking the magnitude of a vector. And then we just try to integrate over the space, over everywhere, over the universe. Then we get the expectation value of my position. So this is how it is calculated. And the expected variables can be anything. So just as I said that here, this is a example about the position, but of course we can just do the same thing for the momentum, for the energy, for the angular momentum, for the spin, for in particle physics we have so much. We have a lot of operators. We have operators for rotation, for mirrored symmetry, for chirality, left-handed, right-handed, for what? For colored charge, RGB, for a lot of things. I don't remember. Oh, for weak interaction, like how to turn a proton into a neutron, or how to turn the positive electron to negative electrons to do the charge conjugate. So we have a lot of expectation values. We have a lot of operators, and theoretical physicists just try to derive it, try to prove it, and try to develop techniques for it. So this is basically how the field theory is interested in. Okay, so this is Schrödinger's idea, and he just developed a framework like this, and then we start to think that way, and we start to develop a lot of things. Good. Then here is a simplest example for you. How do we get the exact wave function? So again, we are doing something like we have to solve a partial differential equation, set up the boundary conditions. We just try to make educational guess on the solutions, and then we try to find the parameters in the solution. We're just generally doing the same thing. We solve a lot of partial differential equations in physics. And this is our model. So we just imagine that we have a box. The particle is stuck in the box and it's not able to jump out of the box. Then this is the environment. This is the size of the box from 0 to L. So this is something like a distance. Then when the particles are moving around in the box, it has a energy E. Okay, so this is for the particle. And we just said that the particle is not able to jump out of the box, and which means that we have potential energies on the walls of the box, and the potential energy is infinitely large. So no matter how fast the particle is jumping around, or no matter how hot the gas is, and but the energy in the particle itself is never large enough to overcome the to overcome the potential energy. So the particles can exist here, they can move around here, they are sort of free, they have to follow several rules to fit themselves into the boundary conditions, but the particles are not allowed to exist here and here, so they are not able to be here and here. This is the environment. And now we would like to derive the wave functions for such a particle in such a environment. So what do we do? And this is our boundary condition and our educational guess. We start from the boundary condition. And I just said that the particles are not able to be here and here. So the possibility for them to exist is simply 0 since the boundary. So from 0 on to a negative directions, all of the phi should be 0. And when the position is larger than L from this point on, all the wave functions should be 0. And just on the boundary, phi of L is equal to 0. So this is our boundary condition. And to satisfy such a boundary condition, the easiest solution is the standing wave. So this is a solution as a standing wave. So from the beginning and at the end of our standing wave, phi can be 0. And this, in the space here, we can have a lot of combinations. We can have a pi of wave, we can have a 2 pi of wave, and we can have a lot of different kind of choices, and all of them are merged together. And all of these different kind of choices is linked with the wavelength of it. So this is how we get the reasonable wavelength of our standing wave. You can just see that in order by a pi. So this is half of the wave or a full wavelength, and etc. And the wavelength should be equal to the width of the box, the 2 times divided by the order. Good. So this is how we do the derivation. And then we just put the reasonable wavelength back into our educational guess. Then this should be the general form of our wave function. And we have orders from 0, 1, 2, 3, 4, 5, and on and on and on to infinity. And this is the equation for it. And then here are some checks. So now here we are just applying the definition of Schrödinger's equation. So here we are just doing the integration. This is wave functions, and then we are taking the absolute value and square of it. The 2 should be outside. Sorry, this is a little typo. Please correct it by yourself. And now we are doing the integration over 0 to L, and by definition, this should be 1. And by doing this check, we can find the amplitude of our wave function. We can find the reasonable amplitude of it. So here we are just doing the double check, and we try to get the amplitude of our wave function, and that's it. We have the exact equation for our wave. Right. And this is a graphical interpretation of our solution. So you can see that when I have n equal to 1, 2, 3, and go on, actually it's not ended yet here. We have the standing wave like this, and the other case, and this is another case. And then the probability of our particle wave is like this. So you just get the absolute value and take a square root of it. Then you can see this is the distribution of the probability of our particle. 1, 2, 3, like this. And then when you have various orders and position for the existence are changing different, and you can see that there are some points where there is no probability for the particle to be there, and there are some points where it's easier to detect them. And you can see everything can be constructed by these standing waves, and you can use Fourier transform to do the detailed mathematics if you have a complex distribution of the particle. Okay, so this is particle in a box. Then this is telling you that we can use the particle in a box to model the energy level of a hydrogen atom. So it's just doing the derivation. You can see that here's the definition for the momentum of the particle, and we just try to change the particles inside into what we just derived. So the wavelength, we just change it into the reasonable value which fits into the particle in the box. Then this is the energy of particles at different energy levels. So this is the kinetic energy, then you just put the numbers in, and then you can have the kinetic energy for the particles on different energy levels, level 1, 2, 3. And this is why we start to call it energy levels, because it's in 1 level, 2 level, 3 level, and all of these levels are not really mixed up. If you just have hydrogen, you have clear energy levels, there's no overlap between them. And you can see here is a multiplicity in the energy for various energy levels. So you have the ground state energy 1, and on the second energy level the energy required is 4 times of the ground state energy. So this is the square of the 2 related to the n squared here. And for the third energy level, it should be 9 times of the ground state energy. And this energy difference is measured, these energies, just show them up as the emission of the light from the atoms. And the light has a frequency. And when we measure the frequency of the light, we can convert it to energy by the relation h nu, right? So we just look at the optical spectrums. So this is the optical spectrums. And we check the difference, the distance between each energy levels. And we can just find out, oh, good, they just matches what we just derived by the Schrödinger's equation, right? So this is a great success. And everybody was very happy because we finally get the clue on how to explain the energy levels in a hydrogen atom. And then we sort of start to derive it from the ground, from the wave functions, from the probability of existence, and then the theory and the experimental results just agree with each other. So everybody was very happy, and Schrödinger was very happy too. And what exactly is going on in the atom? So actually you can see that we are modeling the charge carriers in atoms just like they are a particle in a box. But actually around a hydrogen atom, for Bohr, when he was deriving the theory for hydrogen atom, he was just trying to imagine that there are orbitals around the center of the hydrogen atom. This is the proton of the hydrogen atom, and here's the orbital of our electrons. And the electrons, we can treat it as if they are matter waves. Waves. And waves has a wavelength. And in order, these waves need to somehow arrange themselves and then to put themselves into a orbital. And the orbital is a circle. So the length of the orbital is a finite number. So it's not something flexible that can be bigger or smaller just to fit the electrons. It's not that way. So somehow the size of our orbital is just fixed, and the electrons needs to find the right wavelength and needs to find the right sequence and the numbers of them to put themselves into the orbitals. And the only possible way to fit themselves into the orbital is try to form a standing wave. So you can see that this is the first energy level, second, third, and fourth, and then they have to do a standing wave formation and you can just try to imagine the hydrogen atom this way. It's like you have a lot of sending waves and swinging around in the hydrogen atom, and then you can try to count the frequency, or you can try to measure the wavelength of these sending waves in the hydrogen atom, and then you can derive the P and E and the magnetic quantum numbers for all of these electrons around the hydrogen atom. Okay, so actually this is the reason why we can just try to play with hydrogen atom as if it's a box. Okay, I hope you can see the analogy. And for the Schrödinger's equation, and it has a very general form like this. So Schrödinger tried to follow the classical mechanics philosophy. So he just tried to separate the energies into kinetic energy, potential energy, and the summation of them is the total energy. And we have some operators to measure the kinetic energy or to measure the potential energy. So the operators for the kinetic energy is this one, h bar 2 to mass and the second derivative of the position, this one. So here, this is the operator for the kinetic energy. If you play with your wave function this way, and then you are getting the numbers for the kinetic energy. That's the meaning of the operator. And for the potential energy, then it's just U, it's a scalar operator. And then the summation of them should be the total energy. And usually when we are building the models to solve the Schrödinger equations, when we are building an environment to solve Schrödinger equation, the kinetic energy is directly related to the motions of the wave or the positions of the wave, so we have to describe it. And the potential energy is usually related to the boundary of your surroundings, and the total energy is something that you can do some final check. So Schrödinger's achievement, he just derived the Schrödinger's equation. And here are some conditions to pick the right wave functions. So actually the general form of the wave functions are quite limited, because all of these wave functions should satisfy these 4 rules. And it's just he set these rules up to make the wave functions fit into our imagination for physics, to make it reasonable. So you can just, if you're very interested in fundamental physics, and you can try to read the original article, and you can try to understand why he set up these rules this way. So, but I leave it to the students who are very interested in the philosophy of physics. So if you need it, then you can try to understand what's going on. 然后这边我特别说一下，就是薛定谔方程式，它必须要符合这4个条件。然后它要符合这4个条件的数学形式或是那个波的形式，其实也蛮有限的啦，也就没有很多，大概就是那几套了。对，那如果说同学你是对物理学的历史，或是对量子力学的哲学很有兴趣的话，那你可以去研究一下，就是薛定谔他是基于什么理由他决定要设定这4个条件。那如果说你是真的很有兴趣的同学，你可以去研究这块东西，因为搞不好有一些新的发现会从这里会爆出来。但如果你只是纯粹做一些技术上面的运算的话，就不用太担心，因为你现有的数学工具里面提供给你的薛定谔方程式基本上都会符合这4个条件啊，就是不用背。对，你有需要你再回来看就好了。Good. Okay. Then here are 4 common types of potential energy. So now I'm coming to the point of model building. So most of the theoretical framework in solid-state physics are based on these 4 models. So we are trying to do some experiment, we try to do some observations, and we try to put our situation into one of the models. So basically they work for almost everything. And if you are very talented, or if you would like to be a professional physicist, and you can try to develop your own model. So this is the playground for your creativity. So here are 4 basic models. We have the deep well, so we just derive it, the particle in the box. So actually it's called a deep well, or we can use it on orbits. So this is one thing that we just derived. And here's another case, which is a well, but the height of the well is finite. So the particles inside the well has some possibility to jump out of the well. So this is a slightly modified case. And then here's another case, like we have a barrier, we have a wall, and the particles can somehow jump over the wall to escape. So this is a barrier. And finally, we have the potential energy for a harmonic oscillator. So this is the quantum model for chemical bonds, or for, I don't know, for crystals, periodic distributions. Yeah, periodic potential energy created by atoms, created by protons in the crystal, created by ions in the crystal. So that is the places where we can apply harmonic oscillator. So here are the 4 typical potential energies, and then we spend a lot of efforts on deriving the Schrödinger's equation, which fits into the boundary. Basically it's everything. Then okay, here's a cases, and this is how the wave functions are behaving in these 4 cases. So in a deep well, we have the perfect standing waves of matter, and in a finite well, the particles have some possibility to jump out of the well. So you can see that out of the well, then here are some possibility for them to exist, and it's a little bit like a little tail running out of the well, and the shape of the probability function just distorted a little bit. And then for the barrier, again, because this is finite and the particle has a little bit of probability to tunnel through the well, and then it's getting out of the barrier. So this is the tunneling fact. And here is the harmonic oscillators, and you can see that here's the potential energy created by 2 atoms here, maybe 2 protons around here, and this is the potential energy. And again, we see the structures like standing waves, and then because of the finite number of potential energy, then here are some probability for the particles to get out of our harmonic oscillators. But again, you can see that if you compare this one and this one, you can see the difference. Since the harmonic oscillator has a variation in the length, in the width of the well, right? So this is the L is always, the width is always L from the bottom to the top. But here the width of our well is small, and increasing to a large number, and therefore you can see that the wavelength of our standing wave is changing depending on its energy level. So this is a little bit tricky, and you have to apply some tricky techniques on estimating the wavelengths. So the theoretical chemists, they play around with it a lot. So if you're interested in molecular physics, and then you have to work on it a lot. Okay, then here are the typical cases to fit into these 4 models. So the particle in the box, it's the hydrogen atom, and the finite well, that is the quantum dot. So this is a very hot technique in the recent years. So this is how they are applied in reality. We use the model of the quantum well to derive the behavior of a quantum dot. We are estimating the possibility for the emission of light. You can calculate the wavelength of the emitted light. You can calculate the intensity of the emitted light, and you can play around with your model to estimate what's the best setting of my quantum dot, and then to create a large efficiency. Okay, now you get the link between them. And for the barrier, originally that was derived for the nuclear decay. So, for example, the electrons or the neutrinos is running out of nucleus, and then the process of running out of the nucleus, it's a little bit like they have to run out of a barrier built by the protons. So this is the model that we try to derive the possibility for a nuclear material to decay. And in the recent techniques that is applied on electron microscopy, so STM, scanning tunneling microscopy. If you're interested, you can try to check the physical concept of it. And then for the harmonic oscillator, that is mostly applied in the bonds between the atoms. Valence bonds, ion bonds, 共价键、离子键，还有一个键我忘记了。好，可以提醒我，同学留言提醒我。Okay, so here are the applications of the 4 cases. Then here are the pictures for the applications, and you can look around. So you can see that how reality is related to the models. I hope you can try to imagine and try to find the analogy. 好，然后大家可以看到这个是我有举了几个例子嘛，就是你要怎么样把那些经典的量子力学的模型，然后呢在现实的世界里面我们会用它们来做哪些事情，那大家就会看到说这边有4个 case， 然后下课这10分钟的时间，大家可以想象一下，就是这是现实上面我们会看到的东西嘛，然后他们是怎么样连接到这些量子力学的模型的，大家可以就是休息一下，然后幻想一下。OK， 好，那么我看一下接下来要做什么呢？好，我们先在这边停着10分钟休息一下好了。So let's just stop here for 10 minutes. So let's just have a 10 minutes of a break. So we are 我想一下，要下课了吗？还没耶，要到11点才下课。好，等一下。So let's just go on for 10 minutes, and then let's have the break on 11 o'clock. This is okay. Particle in the box revisited. So what am I doing here? Oh, here. So here I'm just officially applying the Schrödinger's equations and to derive exactly the same thing. So you can see here is the Schrödinger's equation. We have the kinetic term, potential term, and the total energy terms. And since the potential energy is infinity anyway, and let's just leave it. It doesn't matter anymore. And this is the kinetic terms, second derivative of our wave particles. And then we just do a little bit of rearrangement of the particles. And here we have the coefficient, then we turn it into a constant. So you have the k is 2me over h bar, it's just calculations. Then here. Okay, so from the derivations of the Schrödinger's equation, here we have the k, and the k is just the wave numbers. So you can see this is the wave number here. By applying the boundary conditions on 0 and L, it should be 0 anyway. So you can find the number of B, should be 0, and you can find KL, and by definition it should be integer multiplied to pi. So again we are getting into the solution for a standing wave. Again, standing wave, but now here we just see that by the Schrödinger's equation we just get the wave wave numbers before, right? So this is a wave number. It should be equal to n pi, and then by the derivations here, you can just get the exact number of the energy. You're just having exactly the same number. So here we just try to make a cross check between Bohr's atoms model, the model, and Schrödinger's equation. 好，那个跟大家稍微提点一下，就是这一段在做什么。我们在这堂课一开始的时候讲的那个 particle in the box， 我们其实还是在跟着波尔的氢原子模型在做推导。然后这一段其实是呢，我们想要用那个薛定谔方程式测试看看，我们会不会得到跟波尔一模一样的结果。好，所以呢就经过了薛定谔方程式的推导之后，我们发现啊，对没，它的那个微方程的结构是长得都是一模一样的。然后你得到的参数最后也一模一样，所以你用2套不同的方法，可是你到最后会得到一样的结果，那这样就 OK 了，就表示薛定谔方程式这个形态是 OK 的，是可以的。好，那我们在这边我们就先休息一下，休息10分钟，然后10分钟之后我们就是再开始go through 那个其他3个模型。好，休息10分钟。So let's take 10 minutes of the break. 休息10分钟的时间到了，那就是提醒一下，等我一下。现在有来上课的同学，就是有正在看那个直播的同学啊，你可以在直播画面右边有一个聊天室，你可以留言，请你留言，然后留下你的学号。名字的话可能要考虑一下，因为如果你不介意暴露在 internet 应该是没关系啦。对，但是就是麻烦留下你的学号。那我们就是开放让大家签到11:20，因为我就觉得就是现在状况这么艰困，然后又学期末考又很忙，然后到现在还可以很规律的来上课的同学真的是蛮厉害的，很有纪律，意志力很强，帮你们加个总分1分鼓励一下，所以就到11:20为止咯。正在 follow 直播的同学，请你要记得那个留言签到，我会跟助教讲说，请帮你们加分。Okay, so if you're watching the video right now, and please just leave a little message, a emoji, or anything on the chat room on the right panel of our screen. If you see it, please just leave your message there, and then please just leave your student ID there, and you can get one credit of the total rate as a bonus for attending the course regularly. Yep. Okay. 4 models, and then we go on with detailed mathematical techniques in these 4 models. 好，然后那么刚才我们有先讲过 hydrogen atom， 然后再来就是这个是我们刚才有先讲过那个 particle in a box， 然后呢再来就是呢量子井，还有量子屏蔽，然后还有量子力学世界的简谐震荡。这3个模型我们再分别稍微讲一下它的数学的细部，就可能没有办法整套走完，因为它里面你光看那个波的形状你就知道其实它的数学的功课会很多。那我们今天没有办法很细致的把它全部走完，但是我大概提点一下在干嘛。好 Okay, so here is a particle in a well. So now it's not a box anymore. Now the potential energy here, it has a limited number, so it has limited magnitude. And now the thing is, here are particles moving around in the well here, and if the energy is high enough, so if the total energy of the particle is higher than the potential energy, then there are possibilities for the particle to set itself free. So it can be free, it can be jumping out of the particles, and it just jump out of the well and it just run away. So this is possible. And but here on a range here and here, because of the potential energy, then the particle is not able to be there. So this is an interesting situation. And now the process to do it, again, we start with Schrödinger's equation. So Schrödinger's equation, and then we just do a little bit of arrangement. But now we have to keep the term of the potential energy, and we care about the difference between the potential energy and the total energy. And here are some skills to solve it. So you can see that here is a coefficient. The term is a coefficient, and then we just give it a name. We call it the capital C. And now again we see the partial differential equation for a harmonic oscillator, right? So we see it again. And here, this is how we do the educational guess. And again, we see a lot of exponential functions, and C can be real number, it can be imaginary number. If it's a real number, then it's related to a saturation term or a decay term, and if it's an imaginary number, then it's related to the oscillation. So now you can try to imagine all the possibilities in your head. 好，然后呢，大家可以看到，我们又看到那个很熟悉的。好，跟大家讲一下点在哪里。这个点就是呢，如果说你的 particle 是在一个深度有限的井里面，我们现在在乎的点就是呢大重点，就是我们的 potential energy 跟 total and particle 的 total energy 跟环境的 potential energy 这两个能量之间的差有多少。好，所以这就是为什么我们会设定这样子。但是你看一下这个 term， 它是一个常数，它就是一个常数，然后它是环境决定的，然后或者是你给你的 particle 多少 energy， 它就决定了。然后所以你可以直接把它就换成一个代号啊，你就把它当成是一个常数处理就好了。然后我们又看到了在物理学上我们最熟悉的好朋友，我们的结构就是一个2阶的微分方程式。然后呢，我的微function微分2次之后还是它自己。对，那我们又发现同样的事情，你就会看到我们猜到的，我们拆解，我们就会从 exponential function 里面去想。那么也是一样我们熟悉的过程。假设说你的 exponential function 这个 c 这个常数，如果它是实数的话，那它就有可能是变成一个会暴涨的项，就是会增长的项。然后或者是它可能会是一个衰减项，对吧 ？exponential minus， 然后 x 就是它会对 x 它会衰减。那假设说你的 c 是一个虚数的话 ，imaginary number， 你的 exponential 就变成 Euler's equation 了，然后你就会变成你会有很多 cosine 跟 sin， 然后全部排列组合在一起，所以就会变成你有震荡项。那你看到这个东西的时候，你就会知道说，哦，所以现在 possibility 很多呢，它有可能会增长，有可能会衰减，然后也有可能会震荡。然后呢，它的衰减有多少，它的增长有多少，它的震荡有多强，那这个就是你的井的深度，它会去决定，然后或是你井的位置等等等等，它会决定说这几个 term 会怎么样分布。那这个就会是你怎么样去界定你的 boundary condition 的问题。Okay, and this is the general form of our total solution. You can see here's a term which is making the wave function increase. This is the term for the decay. And this is the term for oscillations. We have sine terms and we have cosine terms. So this is the general solution. And by applying the boundary condition, you can get the A, you can get the B, you can get the C, you can get F, you can get the G, you can get K. So you need a lot of boundary condition, isn't it? 然后大家知道我为什么看了我会觉得很好笑吗？因为你可以看那个 general solution， 然后你现在有 A, B, C, F, G 跟 K， 哇，你有好多参数哦。那你要找很多 boundary condition 帮你把这些参数全部都求出来耶。就是你可以算一下你到底有几个 boundary condition， 就有点好笑。那它的问题就是呢，你在设定你的井的时候，你在设定你的量子井的时候，你就要很谨慎。然后你的井的条件你一定要设定的很清楚，就是它的尺寸啊，它的深度啦，可能还有一些别的吧。对，然后你可能就是你要很明确的界定，你要把它的 boundary condition 统统都找出来，不然你会找不出你的 solution 是什么。哦，这题难很难。Okay, and then but anyway, but no matter what the path is, no matter what the boundary condition is, but finally you will get to some solutions like the blue curves here. So you can see I have energy levels, I have different zones where I have zone number 1, number 2, and number 3. In 1 and 3, it's in the position of the wall. Then though it's a wall and the particles shouldn't be there, but because of the wave properties like diffractions, and then you'll still have some possibility to get the particles run through the well and be here like a ghost. So this looks a little bit funny, but somehow this is how the little particles works. And then in the places where the particles can move around, can jump around, you can roughly see the structure of a oscillation. So then here is another important property that you have to try to match your wave functions here and here. So you have to keep the continuity here. But that's another story in the solution. You really take a lot of time on matching the solutions here, but that is another kind of boundary condition. So probably that's the reason why you can finally solve it. 好，然后大家看到这个 solution 的话，有几个有趣的点啊。第一个有趣的点就是你大概还是可以看到你的wave function会有一个能接的结构会跑出来，然后呢你基本上还是看得出来它本来是一个驻波，但是因为一些有趣的原因驻波的形状变形了。然后再来其他一个有趣的地方就是呢，在这个量子井的墙壁里面，就是呢我们在现实的世界里面，就是不是现实，这个也是现实，但是在巨观的世界里面，就假设说你把自己当成一颗巨大的 particle， 你给弄扁，就是你去撞壁的话，你是没有办法穿破墙壁然后站在墙壁中间的，对吧？那要么就是你要拿一颗铁锤把你的墙壁敲开，你才可以把你自己卡在墙壁里面。然后可是对于一个在微小的微观世界，就是比方说电子的物质波这种状况的时候呢，电子它是有机会可以在不撞破墙壁的状况底下站在墙壁的中间。对，那这个就是呢，它因为你的位能它的高度是有一个限制，然后呢就让你的电子变成说，假设它冲得很快，它的能量很高的话，它是有机会可以闯出来的。然后呢你就会看到这是衰减项造成的效应。那么我们在求解的时候，在这里我完全没有表现出来，但是在量子力学在求解这一题的时候，有一点痛苦的题目，就是你要想办法把井里面的波函数跟井外面的波函数这边的连续性，就是你要想办法让它连续，它才会是合理的，就是不能搞成一个状况是我的波函数到这边的时候，然后到这边就因为突然跳了一个数字，然后两个不连续，就是这在物理上不合理。对，所以那我们会在求解的时候会花很多时间去做这个 wave function matching 的动作，所以那也算是某一种程度的 boundary condition 啦。对，所以你就可以知道说，好恐怖，我们现在有好多参数，然后我到底要几条 boundary condition 才能把它全部求出来？其实好吧，它的 boundary condition 其实蛮多的，它要满足的条件其实挺多的，所以到最后我们还是可以解出一个合理的解释来。好，所以这个就是所谓的量子井。然后so this is the so-called quantum well. And the thing is, we can come back to the pictures here. So you can see the quantum. Usually when you do it in semiconductor techniques, and then it's a little bit like you are making little defects in your semiconductor crystals, and those defects created the effect of a quantum well, and then you can let the charge carriers get trapped there and then jump out of the quantum well, and then those falling in, jumping out process is kind of emitting lights, or it's kind of absorbing lights, and then this is why we can create some glowing, colorful texture with the materials with the quantum dot. So you can see those colors, which is actually light with different kind of frequencies. They are components here and here. So this is the reason why we apply it on the researches of the quantum well. Good. Right, and then this is another kind of, this is typical, this is tunneling effect, but the concepts are just roughly the same. We just try to use the waves to describe material wave here, you can still see the wave function, right? So this is a sine wave, and here's another sine wave, but just in the wall, in the barrier, and there are some possibility for the particle to exist here, and somehow they can find a pathway to go through the wall and get out of the wall. And again, we have to apply boundary conditions. We have to keep the wave functions continuous. And because of these boundary conditions, then we can get the forms of the wave functions here. And then finally, we can see the tunneling effect. This is another difficult topic in quantum mechanics. We have to go through a complicated process to get a waveform like this. Yeah. So this is a achievement. Very difficult. I still remember how hard it is. Good. Okay, tunneling effect. And okay. But then we come to the point to do a comparison of matrix mechanics and wave mechanics. And this looks terrible, but it's okay. Don't worry. I try to explain it to you. 好，我们终于到了最恐怖的一张投影片了。这边我想要给大家看一下，就是所谓的波函数的力学，还有矩阵力学这两个东西，他们其实是在处理完全一模一样的问题，只是他们用了2套不一样的数学工具，而且其实他们2个是完全等价的。那我这边是做了一个整理，让大家看到说为什么他们等价。这张投影片符号很多，看起来很可怕，但其实他讲的故事很简单，就没有那么恐怖，所以大家可以仔细看一下。So the slide looks very terrible. There are a lot of symbols, and it seems very hard to follow. But don't worry, the story is simple. So I try to explain what's going on here. We start with the wave equations. So we have some idea about the wave equations. We start with the wave equations. So the wave equations is like we have a parameter. We have a variable to measure. So we call it a state of the system. And the system can be a composition of a lot of particles, like a lot of electrons, and then we call it a system. So the state of a system means that right here, right now, there is a situation. So the situation can be the distribution of the electrons right here, right now. So we call it a state. 就是所谓的态是什么意思？这也是有点抽象。就是呢，假设说我们现在有很多颗电子，每一颗电子我们都用一套那个波函数去形容它们，然后呢，在现在当下这个瞬间，那个电子在空间中会有某一种分布嘛，然后还有某一种不确定性，对，就是不确定原则，大家记得，就是他们就是那它现在当下的存在会有一个状态，然后那个状态我们在英文跟在德文里面就叫它 state， 德文是叫 Stunde， 然后我觉得这是一个非常德国的思维。对，然后在英文里面其实很少有人会说什么什么状态，我不知道为什么，在中文里面也很少会说什么什么状态，所以我们通常在讲到 state 讲到顺德的时候就会说什么意思，搞不懂。对，那个状态就是呢，你可以想象你现在有一台照相机，然后你就啪嚓拍一张相片，然后那张相片里面有什么东西，它们分布在哪里，它们现在在做什么，这个就是状态的意思。好。So a state of the system. Now we are describing a present situation of a collection of particles. And now here we are just trying to describing the behavior of those particles with different wave equations. So each wave equation is related to a particle, and we have 1, 2, 3, 4 n particles and as a collection collected together. And the state of the system then is just a superposition of all of these wave functions. So this is a state. And from the state, we would like to know the probability. So Oh, then here's an explanation here. You can see that here I have state 1 to state n for particle 1 to particle n. And each of the x here is written by wave equations phi of x, and then here's a combination of a lot of waves with different angular frequencies. So here is a state. So you can see the relation between them. And in the form of matrix mechanics, we are writing the state of a system in a matrix. But actually the equations here and the matrix, they are just exactly the same, but they just have different forms. You can see the amplitude c, you can see the wave functions x of n, and then this is the c and this is the x of n, but we are just lining up on a vertical column. So you can see that, oh, they are just the same. They are not so different. It's just the same thing in different mathematical forms. Then to get the probability based on wave equations, then we have to do the multiplication of these waveforms, and they can be imaginary numbers, so actually we are taking a conjugate of them. So this is how we do the calculation, and finally we get the amplitude for the probability. And then in the matrix mechanics, we're just doing the same thing, but in the matrix form. So when we are doing the multiplication to get the probabilities, we have a vertical matrix, we have a horizontal matrix, but we are just doing the multiplication of them. And finally, you have a summation of a lot of amplitudes, and then you have the total probability. So these two equations are just doing exactly the same thing as this one. We are just doing the square of the amplitudes of a wave function, and if we do the integration over a universe, and then we get the probability should be 100%. It's just exactly the same thing. And when we are doing a measurement, which means that now we are working on a observable. The observable will be a operator in mathematics. Observables, and what are observables? For example, position is an observable. Momentum, energy, angular momentum. So here are the 4 typical observables, and all of these observables have their own operator. Then the position of the operator in the math will be on the position of A. So you can see this is the A, this is the wave functions, A and wave functions, and you can see the summation of all of these waves, and it looks very terrible, but don't be afraid. You go through all of this process, and then you can get the result, and then you can get the value that you will measure. So this is the value of the observable, which you can measure it by a detector, or this is the position of the particle that you see on a diffraction pattern. So so this is how we do the calculation for the observables. Then in the matrix mechanics, we're just doing the same thing, but in a matrix form. So you can see the observables here, you can see the vertical matrix, horizontal matrix, and for the observables, then it will be a x by x matrix. It depends on how many energy states you have in your wave functions, and then you can see their geometrical relation, right? So you can see the observables, and then you can try to calculate so how many positions in the matrix is there, so you can count. It's a m by m matrix, and it depends on the states in your wave functions. But finally you will get the result. And in the matrix, in the math of matrix, and the process here is called, you are calculating the eigenvalue of your matrix. So this is the eigenvalue of your matrix. Eigenvalue is German too. Eigenvalue, what does it mean? Eigenvalue 是德文，但是 eigenvalue 在德文里面是什么意思？我忘记耶。拍摄我自己是用德文学 quantum mechanics， 可是我忘记 eigenvalue 的德文，在德文它的意思是什么？让我查一下。eigenvalue， 对啊 ，eigenvalue 是什么意思？特征值对，特征没错。eigen 在德文里面 ein 是一个嘛，是个体的意思。eigen 就是一个个体， 然后一个个体，你之所以可以叫它说它是个体，就是因为它有特征。对，所以 eigenvalue 就是特征值的意思，就是你现在这个 state 它有某一个特征，然后那个特征，然后你就拿着仪器去测量它。对，所以 eigenvalue 就是特征值的意思。So eigenvalue in German it means characteristic value. So Eigen in German means one entity or one individual thing. And you can call yourself individual because you have a special character, you have a special property. You are the only one who has that property, right? So you can call yourself individual. And eigenvalue just means that this is a characteristic property. It is a character which shows your individuality. So this is called eigenvalue. So it means that the state has a special character which you can measure, and then you just take your experimental devices to do the measurements, and then you can get the value. So we call it eigenvalue. So that is the characteristic properties of something. Okay, so I hope you can get it. This is highly philosophical. 就希望大家可以理解那个德国人的逻辑是什么。这真的非常非常的哲学性，非常非常的逻辑性。这德国人就是这样可怕。就是那德语世界长大的人，我觉得应该是因为他们的语言的关系，然后他们做什么事情都很有逻辑，然后做什么事情都很有哲学性。对，好 ，OK， Yep. So here is a comparison of wave mechanics and matrix mechanics. So you can see the wave functions, and you can see the matrix form of wave functions, and you can see the operator for momentum, which is P. You can see the operator for energies, and then you can see the symmetry between the two forms. And actually they are just exactly the same, but they are just using different symbols. Yep, and here's the point with uncertainty principle. I think in the last lecture, in the chapter for the matter wave, and I just tried to explain the uncertainty principle in the form of superposition of different kind of waves. So you can you always have a range of wavelengths, you always have a range of positions. And I find that interpretation is really good because it's very solid, and it doesn't contain any ambiguities, and it doesn't have the ambiguous point, so you can just stick with that interpretation. And in case of Heisenberg, this is a big problem. This is a pain in his ass, really. So he just discovered the uncertainty principle when he was playing around with his math, and then he just find that this is very, very tricky. So you can see that here we have two operators, and I would like to operate them in a sequence. But Heisenberg was checking, for example, if I do the calculation on X first and then do the calculation on P, then I will get a result, right? And then if I do it in another order, if I do the operation on P first and then do the operation on X, am I getting the same results? But in his mathematical forms, he just find that no, this is very, very painful. So he just find that, it doesn't really matches the fact that we are very used to in classical mechanics. In classical mechanics, it doesn't matter if you do X first and then do P, or you do it vice versa. It doesn't matter. But in case of quantum mechanics, it do matters, but he cannot explain why. So the only solution for them, for him at that time, is like he has to relax his solution a little bit, and then he has to introduce a little bit of uncertainty in it, and then he can say that maybe the difference between maybe the difference in the commute is due to the uncertainty principles, and then because he works on the spectrums of the atoms, he was working on atomic spectrums, so he just tried to define the width of my uncertainty in the language of spectrums. So he is just using the full width of the half maximum of his spectral line, and then he just tried to set a number for the uncertainty that he can tolerate. So that's the reason why I just remind you that the point is we have a range of x, we have a range of p, but here is a range, and it doesn't have a specific number. It just depends on how much uncertainty that you can tolerate, and then you can just set your definition by yourself. But in Heisenberg's form, it's very hard to give the strange mathematical flaw a physical meaning. So maybe that is a little weakness of the matrix mechanics. Okay, this is the story about uncertainty principle. And then I am coming to the strange point about Copenhagen interpretation and the cat states. So we start from the Copenhagen interpretation first. So you can see that now this is the point with a light, with a photon, or with an electron. And now this is the famous double slit experiment. For either light or electrons, we can see that the light or the photon or the electrons here, it's running this way, and you can say it's a particle of electrons, or you can say this is a planar wave. You can use these two forms to describe it, no problem. And now the wave is passing through the double slit, and it's creating the diffraction patterns, and because of the interference of these diffraction patterns, then we get the probability distribution of our electrons. And here we can see that here are more possible, this is less possible, more possible, less possible, more possible, and we can see the fringes. So this is what we see from the experiment. We can see the positions of the particles or the possibilities of the particles, but we are not able to see the waves here, the gray lines here. This is just in our head. We are not able to measure it. And now the question is, okay, it works for electrons, it works for photons, but does it work for cats? You can play with the cat at your house. You have a cat, and you just set two little doors, and you just ask your cat to pass through the door, and if your cat follows your order, if it obeys, you can just imagine that, okay, my cat will choose one of the slit and walk through it, and then land himself on a position, right? You are not going to see a diffracted cat. You don't see the interference of the cat, and then you don't see three cats standing on the most probable point, right? In the real world, with big identities, animals, humans, any kinds of materials that you can touch and you can see, and all you can measure is the result of the probability. It's just one case. It's not superposition of a lot of cases, and for the one entity you don't calculate the probability. Just like now we have issues with the virus, and every day you see people dying, and every dying person is just one person, it's just one individuality. And it's very strange if you are applying mechanics right now, though we are applying statistics right now, and though we are still applying the statistics and try to control the virus, but every dying people is an individuality, and for himself and for the doctor, it's just one case, the one only case that we are working on, right? So now we have a strange inconsistency. between on the individual ones and the statistics. So what's the bridge between them? And then here comes the Copenhagen interpretation. So those people, they just said that I think you are too picky between these two situations. Let's just stick with the measurable facts. So if your tools, which is wave function, if the tools is giving the right fact, then it's a good tool. So what's the point for you to challenge it? You don't need to be so picky. You don't need to be so politically right. You can just use your good tool. You can feel happy, and let's just stick with the measurable effects. And then they will develop a belief or a thoughts like the wave function and the states, they are just mathematical tool. We don't need to care if they exist or not. So this is the Copenhagen interpretation, and based on the Copenhagen interpretation, we are still using the matrix and we are still using the wave functions to derive the optical spectra, to derive the transitions of the electrons, to derive the intensity of light from the quantum dots, to derive the current from the tunneling effect. So we're just deriving the measurable facts, and we don't really care if we can measure the wave functions or not. So now the modern technology, most of them are built on the Copenhagen interpretation, which is very weak actually. And so Bohr just would like to say that Bohr is a Danish scientist, and he lives in Copenhagen, and he has a lot of students. So that's why we call it the Copenhagen School, and we call it the Copenhagen interpretation. So he just said that, okay, I think you see one specific photon, one specific electron, because you measure it. So just like the doctor, he work on a dying people, and the people is dead because the doctor tried to work on it, but it doesn't work, and so the people is dead. So you see one specific case because you measure it, because you work on it. So this is the Copenhagen interpretation. This is what the practical people are thinking. But Einstein is not satisfied with it. Einstein said, I find it really ridiculous. So something exists and it just exists. So something happened, it just happens, even if you are not looking at it. So he is giving the example like the moon is always there and it just rises, it falls, and even if you're at home, you don't have time to look at the moon, but the moon is always there. So he just finds the Copenhagen interpretation very ridiculous, and he just said, no, I don't agree with it. So we should find another interpretation that doesn't work. So this is Einstein's oppose to the Copenhagen interpretation. So he just would like to say that the measurement shouldn't decide the outcome. So the outcomes is going on his way, and you are not the God. You are not deciding anything by doing the measurement. So this is the point. And Schrödinger is thinking about it too. He basically agreed with Einstein, but Schrödinger has kind of humor. He is not the people who are picking up fights and doing a lot of arguments or fighting with people. He's not that kind of person. He would like to show you how ridiculous it is with a strange story, which is the Schrödinger's cat. So he just developed a little story about it. He just said that, okay, now we have a box, and in the box we have a radioactive material, and the radioactive material can emit some electrons from it. So we are in a quantum case, and once the electrons is running out of the material, and it just hit into a detector, and the detector start to push the toxic gas into the box, and the poor cat is in the box. And he just imagined that, okay, the Copenhagen interpretation is telling you when the box is closed, we are not sure if the cat is alive or dead. So we have a state. The state is a composition of a living cat and a dead cat. So the two states are mixed together. They are superimposed together. They are tangled. And in that state, we don't know how to distinguish them. So the cat is living in a state that the life and the death are a mixture together. So everything is mixed. We are not sure what's going on. But when you open the box and when you just look at the cat, and suddenly you decided if the living state or the death state is going to be manifested into reality. And isn't it ridiculous? So Schrödinger is telling you the story because he would like to show you that the Copenhagen interpretation is strange. Even if we are working with the quantum materials, and that interpretation is strange. He wanted to tell us the cat is alive or dead is already as it is before you open the box. So when the electrons are running out of the radioactive materials, when the gas is running everywhere in the box, the cat is already dead. So it's already decided before you open the box. And the observer shouldn't decide if the cat is alive or dead. So Schrödinger would like to tell you this by a very funny story. And it's a little bit like, I think it's a little bit like the people right now on the internet. So sometimes we would like to fight a ridiculous ideas in a funny way. So we do it ironically. It's like you are you are acting like those people who you don't agree with, and you are just trying to push their arguments to an extreme border to show how ridiculous it is. So this is what Schrödinger was doing. So actually he didn't tell the story about the cat very seriously, but somehow the people take it seriously. So at the moment we have a lot of experiment on photons. So people are testing the cat states of photons, and people are testing cat states of electrons, atoms and electrons, and here are a lot of experiments going on. So I think in physics this is a strange moment. I'm just checking the cat states and you can see what it is. Cat states. So this is a little bit ridiculous, but somehow we are getting serious, and then now we have so many experiments about it, and people are trying to understand why the quantum states are tangled and why they separate themselves. For example, the living cat, the dead cat, they are a mixture, right? And what is the reason why the two states separate, detangled, and finally one of the states disappear and the other state just turn into reality? So people are very interested in the process, and they are trying to give us new theories about it. And here are a lot of topics about the bonded states, the tanglement, detanglement, and what's the bridge between the quantum world and the microscopic worlds. Okay, so that's it. We are still working on it. There is still many interesting topics in physics to work on. Okay, good. And if you're very interested in these philosophical topics in quantum mechanics, then you can pick the topic number 2 for final exam. So I just recommended a talk from theoretical quantum mechanics. A professor just talked about it. So you can just watch that video, and then you can try to understand, and then you can try to write a summary report about it. Okay, well, so now we are at the end of the lecture and we are at the end of the 1 year general physics, and I hope these knowledges and those techniques will prepare you, will help you to solve the problems in your future works and in your future lives. And if you're very interested in these topics, and I really encourage you to do some researches on physics, so it will give you a lot of interesting things and interesting thoughts in your life, and you will have a new perspective when you are looking at the nature, when you are working on the materials around you, and that will really help you a lot. Okay, so thank you very much for your attention, and then I hope you I wish you happiness in the future, and of course keep yourself safe and healthy. Okay, so that's the end of the lecture. Thank you very much for your attention.